Hello everyone, my name is Kuldeep and today we'll be talking about a very interesting problem in natural language processing. It's called part of speech tagging and it's used almost everywhere where you do natural language processing. It basically means you'll be tagging the words in a sentence with their grammatical category. For example, in a sentence there can be a verb, there can be a noun, there can be a proper noun, there can be a modal verb, adjectives, so on and so forth. So if we take an example, as we said, part of speech is just tagging sentences with the respective part of speech. Let's try and do one with example. Let's say John has a small dog. And in this, we can easily see that John is a noun, has is a verb, and a is a determiner, small is an adjective, dog is a noun. So noun, verb, determiner, and adjective here are parts of speech. So we'll be trying to have some label data in which noun, adjective, determiner are already mentioned for every word, and we'll be trying to predict that for unknown sentences for each and every word what the grammatical category is. But before we go and learn about parts of speech, we need to understand what is the significance. Why are we doing it, right? So parts of speech is very readily used around the natural language processing pipeline, and you can easily see them in spelling checkers, in grammatical checkers. So for example, there's software called Grammarly, and you must have seen the ads for that, and it does the grammatical checking and spell checking for you, right? So there will be in the backend a part of speech model running. So this is just a basic example why we are doing part of speech analysis, why we are trying to learn that. So we'll be going through various ways in which you can do parts of speech analysis, various ways how you can tag parts of speech in a sentence. But our end goal will be to learn the state-of-the-art model that is present right now, that is Hidden Markov Model. Before I start, I would suggest that even though you might be thinking that you need a lot of grammatical knowledge, you might think that you need let's say MSc in English, but you don't. You just need to have a basic understanding about what the verb is, what a noun is, and that's it. Rest model will take care for you. There can be various parts of speech in a sentence, but for simplicity, we'll be trying to do with just three parts of speech, basically noun, which can be a name like John, car, India, apple, dog, and house. Just for example, then we'll be looking for modal verbs, which will be must, will, can, may, would, right? Then we'll be looking for verbs. Verbs are basically actions like running, swimming, talk, eat, speak, etc. So we'll be looking for these three parts of speech in a sentence and try to guess what each and every word has the category in the grammatical space. Let's say there are three friends, Mary, Jane, and Will, and we want to tag the sentence Mary saw Will. And since we need some label data, we have label data as follows. Jane saw Will, in which Jane is a noun, saw is a verb, and Will is obviously a noun since Will is a friend and it's the name of the person. And we also have Mary saw Jane. So we'll be using our label data to predict each and every word's category in Mary saw Will. So our first algorithm is very naive and very easy, in which we'll be trying to use the most common part of speech associated with a word. So first what we'll be doing is we'll be collecting the data, which we already have. Then we'll be creating a lookup table. So what is a lookup table? We'll be tagging each word with the most common part of speech that is associated with that word. Then we'll be taking a target sentence, basically the sentence that we are trying to figure out the part of speech for, and we'll be going word by word and tagging the most common part of speech associated with it. And that's it. So if we go with our data, so we have Jane saw Will, Mary saw Jane, and in that we can see Mary occurred once, and that once it was noun. And saw occurred twice, each and every time it was a verb. Jane occurred twice, each and every time it was a noun. And Will occurred once, and it was a noun as well. So looking at the lookup table, now we can find for each and every word the most common occurring part of speech. So first we go for Mary. So Mary almost each and every time, so most commonly it occurs as a noun. So we'll say that Mary is a noun. Saw always occurs as a verb. So we'll say saw is a verb. And will always occur as a noun. So we'll say will is also a noun. So this seems pretty straightforward that we have to just go word by word and look for the most commonly occurring part of speech. But this is way too simple, don't you think? And if I say this won't work all the time, can you think why? Let's take another example. So again, we have three friends, Mary, Jane, and Will. But now our label data has broadened and we have Mary will see Jane, in which will is a modal verb. Then we have will see Mary, in which the first will, since it is the name of the person, is a noun. Then we have will, which is a modal verb, and see is a verb, Mary is a noun. And we also have Jane will see will. And this time we'll be trying to predict the parts of speech tags for Mary will see will. And first of all, obviously we'll be creating the lookup table. So Mary occurred twice, and each and every time it's a noun. See occurs thrice, each and every time it's a verb. Jane occurred twice, each and every time it's a noun. Will occurred 5 times, and it was a noun as well as modal verb, but most commonly it occurred as a modal verb. Now let's go and tag each and every word. So Mary is pretty straightforward, it always occurs as a noun. Will is a modal verb because will most commonly occurs as a modal verb. See is a verb, it always occurs as a verb. But now we come to the name of the person, will, but it's a noun. But our lookup table says it's a modal verb. Can you see the problem? That for each and every word, it will always give the same answer. For every particular unique word, you'll always get the same answer, be it that the context for that verb might be different. So now we can answer why this won't work each and every time. Lookup table with just a single word does not consider the context that the word is used in. So as the problem statement broadens, and almost each and every time in real world, you'll be considering the context, because most of our sentences are based on context. So how can we consider the context? One of the ways in which we can consider the context is basically using bigrams, in which we take into consideration how the word was used. Basically looking at each and every word's neighbor. So each and every time looking for the neighbor, we'll be creating a lookup table again, and we can see Mary will occurred once, and at that time it was noun followed by a modal verb. As in the same way, will see occurred thrice, and each and every time it was modal verb followed by a verb. So on and so forth, we can create a lookup table. Now let's move on to a sentence. So the first word that we'll be tagging, we'll be using the previous lookup table that we already created. So Mary, almost each and every time it occurred as a noun, so we'll tag it as a noun. So for each and every following word, we'll be using this lookup table, and we'll be considering how the word was followed by, and basically considering the neighbors and the context that the word was used in. So if we go for will, Mary will occurred once, and in that time it was noun followed by a modal verb. So we'll say that will is a modal verb. So in the same way, we'll go on and tag all the words. So will see occurred thrice, and when the will we have to consider that will was a modal verb, it occurred thrice, and that time see was considered as a verb. Then see will only occurred once, in which the see was a verb, and then will was a noun. So now we have tagged Mary will see will correctly, and we have also considered the neighbors and thus the context in which the word was used. So we have correctly labeled one will as a modal verb and the other will as a noun, which is correct. Now this seems the perfect algorithm, but if I say that this algorithm also has some problems, right? But you can even extrapolate on that. Let's say instead of using the bigrams, you use trigrams. You can even experiment in using the both lookup tables for one word as well as bigrams, trigrams, basically n-grams, and find out the perfect match that works for your test data as well as your training data, right? You can even use the previous table as well as this table in conjunction, so that one table corrects if there is a wrong prediction made by the other table. So now, since you are able to use n-grams and the lookup tables pretty efficiently, let's spice up the problem a little bit. So already we had 3 friends, Mary, Jane and Will, but now there is another person in the mix, Spot. And our data, our label data is containing Mary Jane can see Will, Spot will see Mary, Will Jane spot Mary, and Mary will add Spot. And the target sentence that we are trying to predict is Jane will spot Will. So now again we'll be creating a lookup tables, we're creating a table with bigrams, and now we have got a problem. If you see, in all the cases, Jane followed by Will never occurs in a training data. And now we have no way of knowing what Jane and will be if we know one of the neighbors. So wherever there is a problem, there is a solution, and I think this is the best time to consider the hidden Markov model. So the hidden Markov model is a probabilistic model in which we'll be considering the probabilities. So there are two probabilities that we'll be using. The first one is the transition probability. What is that? So it's how likely is that a noun will be followed by a verb. So basically, how likely if Jane is a noun, the next word that occurs is also a noun or also a modal verb or also a verb, right? So how likely is a noun followed by a modal, or how likely is a modal followed by a verb, or how likely is a verb followed by a noun? The second probability that we'll be considering is the emission probabilities. So how likely is Jane will be a noun, or will it be a modal, or will it be a verb? So this is emission probabilities. So considering these two probabilities, we'll be using the hidden Markov model. So first let's work on emission probabilities. Before doing that, let's create a simple lookup table in which we just plot out how many times Mary was stated as a noun, as a modal verb, or as a verb. And we can see Mary occurred 4 times, and each and every time it was a noun. Then we go for Jane. Jane occurred twice and it was a noun all the time. Will occurred 4 times, but once it was a noun, all the other times it was a modal verb. So we'll go on and do for each and every unique words: spot, can, see, and pat. So now let's consider a possibility that Jane is a noun, will is a modal verb, spot is a verb, and again will is a noun. So what we'll be considering is how probable it is that if Jane is a noun, the next word, basically if it is a noun, the next word that will be occurring will a modal. So the probability that a noun will be followed by a modal will be stated as the transition probability. Now, how likely is that Jane will be a noun? Basically, will be a modal and spot will be a verb, and this is our emission probability. So now let's create our emission probabilities. So for Mary, we'll be stating that how probable is that if a word is a noun, that it will be a Mary. So noun occurred 9 times, and out of the 9 times, it was 4 times that it was Mary. So the probability is 4 divided by 9. And so we go for Jane. So noun occurred 9 times and it was twice that it was Jane. Then we go for will. Will was noun once, while the noun occurred 9 times. But will was also a modal verb. Modal verb in total in the data occurred 4 times, and it was 3 times that it was will that was the modal verb. So we go on and create the emission probabilities for each and every word, considering that a word was specific part of speech, and how probable is that the specific word was that part of speech. So if we say that how probable is that if a word is a noun, that it will be Jane. So we can say if it is a noun, noun occurred 9 times and only twice it was Jane. So the probability for that word to be noun and Jane will be 2 divided by 9. So now we move on to the second probability that we have to discuss, and that is transition probabilities. So transition probability is how likely, let's say, a noun will be followed by a noun, how likely is a modal verb will be followed by a noun, or how likely is a verb will be followed by a noun. Basically, how likely is one part of speech followed by the other part of speech. But to do this, we first have to add starting tags and ending tags so that the first word and the last word can also be considered as followed by something. So if we add tags, start tags and end tags, and we create a table in which we state how many times the start tag was followed by a noun. So start tag was followed by noun 3 times in Mary Jane can see will, Spot will see Mary, Mary will pat Spot. So each of these times the start word was noun. So start was followed by a noun, and only once it was that the start was followed by will Jane Spot Mary. Then we go with noun. How many times noun was followed by a noun? So it was just once. When we can see Mary Jane can see will, that noun was followed by a noun. We create a data in which we have how likely is that one part of speech followed by other part of speech. So now we combine the two probabilities, basically the two graphs that we have created to create the hidden Markov model, in which all the words Mary will, spot, Jane will, can spot, and see Pat, even though all the words that occurred are observations, and the hidden states, basically the states that we are trying to predict, are noun, model, verb, and the verb. Observations are what we get from the sentence, the words, and the hidden states are basically that we have to predict from the observations that we have. Between each and every hidden state, we have transition probabilities, and between the observations and the states, we have emission probabilities. So how likely will be a noun followed by a model verb is a transition probability. How likely that a noun is Mary is emission probability. So now what we'll be doing is we'll be going through the hidden states with some probability. So we obviously start from the start and we go to noun. So probability that the start will be noun has some probability, which is called transition probability. After we reach noun, we record the word Jane with some probability. Then we go to the model verb with the transition probability and we record the word will. This is how we'll be generating almost all the sentences that are possible given our label data. So now all we have to do is record the probability that we can generate a sentence, a target sentence with, that is Jane will, spot, will. So again, we'll start at the starting hidden state and then we go to the noun. So the probability that the first word will be a noun has some transition probability. So now since we have come on noun, the probability that the word at this state will be Jane has some probability. In this case, it's 2 by 9 and we record that. So till now what we did is we started at the starting point and we recorded the probability, which is the transition probability that the next word will be a noun, which was 3/4. Then we recorded the probability that that noun will be Jane. That is the emission probability, which is 2 by 9. Now we go from noun to model verb. And now we record again the transition probability that noun will be followed by a model verb, which is 3 by 9 or 1 by 3. Then we record the probability that the model verb will be will, which is 3 by 4. So we go on from model verb to verb, record the probability. What is the probability that that verb will be spot, which is the emission probability. Then we go from verb to noun, noun to the end of the sentence. So now what we do is now, since we have all the probabilities, we multiply them, which is 0.003858. So now you might be wondering, why did we multiply them? Since each and every probability is independent of all the other events. So since how likely that the starting word is a noun has absolutely no effect on how likely is that noun will be followed by a model verb. And that does not have any effect that how likely that model verb will be will. You might also have a question that the probability that we got is very, very small, and you obviously know the answer that we got here is correct. So how can we say with confidence that we got the correct answer? The thing is that we have to consider this probability relative to all the other states that we considered and the probabilities that we got. Let's say we consider the hidden states for each and every observation as noun. The probability for that is 0.00002788, which if we compare with the probability that we got earlier is extremely small. So basically we can compare the probabilities for each and every observation and hidden state combo that we create and pick up the probability that is the highest. So how likely that sentence will have that set of hidden states will take the best possible outcome that we can predict. But now here, can you guess how many probabilities that you will be comparing? So to calculate that, we can say that for each and every observation, there can be 3 hidden states associated with it, which is basically noun, model verb, and verb. So Jane can be noun, model, verb, or a verb. Will can be noun, model, or a verb. Spot can be noun, model, or a verb. And will can also be noun, model, or a verb. So each and every state has 3 hidden states that can be associated with it. So the answer of all the possibilities or all the paths or the probabilities that we have to compare is 3 to the power of 4, which is 81. And how we'll be calculating the total probability for each and every possibility, the 81 possibilities that we just calculated, is we'll be taking all the transition probabilities that a word, the starting word is a noun and that word is followed by a modal verb, so on and so forth, and multiplying with the emission probabilities that we get, that a word is likely to be Jane, a state is likely to be Will, a state is likely to be Spot, and we get the total probability for each and every 81 of those states. Then we take the state that has the highest probability and we will give each and every observation the hidden state that we have got. So since now we have studied part of speech and various ways in which we can tag a sentence with its part of speech, and we have worked with hidden Markov model, you might be wondering that hidden Markov model is not very efficient. So as we can say that there were 81 states, and for each of the 81 states we had to consider all the probabilities that we found and then pick up the largest one. It's very computationally expensive. And also, as the data grows and as the number of hidden states grows and as the observation number grows, the number of probabilities that we'll be comparing will also grow. So how can we go through that? So for that you can learn Viterbi algorithms, the Baum-Welch algorithms. I'll link some resources down below in the description which you can go through. And this is all that you need to learn about parts of speech tagging and hidden Markov models. Thank you for listening to me. Thank you for learning, and I'll see you next time.